Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll be starting the lecture 4B of controllers and compensators. So in the previous lecture we did few questions, mainly they were gate questions, and in this lecture we'll do few assignment questions which are not from gate, but those are very important to clear your concepts. So this type of question may come up in interview, or these type of questions can clear multiple concepts. Okay, so this is the first question where they have given a circuit icon and they have asked us to find the maximum possible phase lead. So they are talking about the phase lead. By that you can assume that this is a lead compensator if you couldn't identify the standard circuit. Okay, even if you don't identify the standard circuit, what do? You find the VO over VI ratio in the Laplace domain, and then you just write the standard transfer function of a lead compensator and then compare the two, and from there you can write the formulas. Okay, so let's do it. So I just want to write VO over VI. Okay, I don't remember anything. I just want to write VO over VI of S. Okay, for that obviously I will simply transform this into Laplace domain. So let me copy this. So basically what will be V over Vi? So it is like a voltage divider, so it will be equals to 1 by 4 divided by simply 1 by 4 plus this 2 by S divided by 2 plus 1 by S, which is equals to, if I multiply this, so this will be 1 by 4 in the front, and if I take the 4, this will be 1 by 4 at the front, this will be 1 by 4 plus, if I multiply S, this will be 2 divided by 2S plus 1. Okay, now what I can do, I can simply multiply 2S plus 1 also, or I can multiply 4 also. So if I multiply 4 with this, the denominator, this will become 1 plus 8 divided by 2S plus 1. Now if I multiply 2S plus 1 on both sides, so what will happen? So this will become 2S plus 9. Okay, so 2S plus 1 upon 2S plus 9. So what is the standard form basically? So if I recall the standard form, it is something like this, that GC of S 1 plus tau divided by S plus 1 by alpha tau. Okay, so obviously we have to make the coefficients of S 1 over here, to make the coefficient of S 1 over here. So basically if I multiply this, I can take 2 common, so this can become S plus 1 by 2 into S plus 9 by. So now if I compare this, so from here my KC will be equals to 1 and tau will be equals to 2. Now alpha tau is 2 by 9, so my alpha will be equals to 1 by 9, which is fine because alpha should be less than 1, which is satisfying over it. And high frequency gain should be equals to 1. So you can just high frequency gain should be equals to 1, high frequency gain should be equals to 1, low frequency gain should be equals to this 1 upon 9. So you can cross verify also. How you can cross verify? So low frequency, what will happen? Low frequency, this will go to infinity, so this will divide in this ratio. So what will the ratio? It will be simply 1 by 4 upon 2 plus 1 by 4, which is 1 upon 9. So yeah, that is fine. At high frequency, this is, sorry, at low frequency, this is getting open circuited, so only this and this are remaining. So yeah, at low frequency it is fine, so it will be this ratio 1 by 9. At high frequency, what will happen? this will get short circuited, so totally Vi will be equals to Vo. So this is also satisfying. So from here also you can cross identify whether you have written your transfer function correctly or not. Okay, so this is Kc alpha 1 by 9. Now alpha you have got. Now you can proceed from here two ways. Either you remember this, that for this is a lead compensator, right? Alpha is coming less than 1, or you can see from here also that the 0 is much nearer to the origin than the pole. Okay, so from here also you can understand lead compensator. So from here you can proceed in two directions. Your omega m will be the geometric means of the 0 and the pole. So it will be 1 by tau under root alpha, or directly from here you can do geometric means of these two. So it will be simply under root, so it is simply 3 by 2. Okay, radian per second, 3 by 2 radian per second. Now let's do the phase phi. So obviously we know that the maximum phase, like at which frequency I will get maximum phase at 3 by 2. So let's just do this. Let's just write the angle formula for this. What will the angle? Simply it will be tan inverse omega by 1 by 2 minus tan inverse omega by 9 by 2 at omega equals to omega m. So you just put omega m over here. What do you get? So if you put omega m over here, you will simply get, this is 3 by 2, so this will be simply 3 minus tan inverse, what, tan inverse 1 by 3. So it will be like always this, that 3 upon 1 by 3. Okay, so now what will be the answer for this? So let me just quickly cross check this. What will be the answer for this? 3 tan inverse minus 0.333 tan inverse 53.13 degree. Okay, so this will be my maximum phase. Now other what a method you could have done is, if you remember the formula of phi m directly. So if you remember the formula of phi m directly, phi m equals to what? Sine inverse 1 minus alpha divided by 1 plus alpha. So what is my alpha? Alpha is 1 by 9. Alpha is 1 by 9. So if alpha is 1 by 9, you directly put over here the value of alpha. Sine inverse 1 minus 1 by 9, which is 8 by 9, divided by 1 plus 1 by 9, which is 11 by 9. So it becomes 8 by 11. So 8 by 11, if I do sine inverse, okay, sorry, it will 10 by 9, 10 by 9, so it will be 8 by 10 actually, 8 by 10 of sine inverse, it will 53.13. okay, so it will be 53.13 degrees. So from here also you can get that how much maximum phase rate you will get, or from here also you can get. So this is the method 1. If you tend to forget that phi m formula, because many people tend to forget that, you can directly derive it from here also. No need to remember that phi m formula, or if you remember, well and good, you can directly use that phi m formula. Okay, this was a very standard question, so very simple question, or you can easily solve. Now this next question, you have to identify the range of frequencies at which we get maximum phase for the given compensator transfer function. So you have to identify the range of frequency at which we get maximum phase for the given compensator transfer function, maximum phase. So we are talking about the maximum phase, so this must be a lead compensator. So is it a lead compensator? Yes, this is a lead compensator, because initially I'm getting a 0, then I'm getting a pole, then I'm getting another pole, and then I'm getting another 0. So first 0, pole, then 0. Yes, this is a lead lag compensator. So there will be a maximum phase component, because initially my slope will be plus 20 dB per decade. Okay, for the magnitude I'm talking about, but for the phase also, my slope will be, initial slope will be plus 45 degree per decade. That's why. So like this, we can draw the rough diagram of both a phase plot, because here what do I see? The poles and zeros are well spaced between each other. Okay, so that's why I can use the concept of Bode phase plot here. Okay, else it would have been very difficult for me to understand the range of maximum phase for a lag lead compensator. So basically we'll use the concept of Bode phase plot. So if I use the concept of Bode phase law, what will happen? So this will be omega, and this will be angle of J of G omega. So let me mark the corner frequency. So at 0.1 I have a 0, so 10 times before that and 10 times after that the effect of 0 will be there. So 0.1 and this is 0.01. This is 1. So and then like 10 times before that also effect is there. So at 0.1 effect is there, then 10 times after this effect is there at 10, and obviously here we have 10, and 10 times after that, 10 times before that, and 10 times after that there is effect. This is 100 and 100, 10 times before that, and 10 times after that there is still effect of this 0. This is 1000. So before this obviously nothing is present, so my phase will be 0. My phase will be 0. Let me use that. Okay, so my phase is 0. Next, what is happening? Then I'm encountering a 0. So effect of 0 will come. Effect of 0 will come. Fine. Up until 0.1. Up until 0.1, effect of 0 has came. Now what is happening? Like this slope is was what? Plus 45 degree per decade. Plus 45 degree plus decade. Now next what is happening? Next at 0.1, like this effect of 0 will still remain, but a effect of pole will also come up, right? Which will contribute minus 45 degree per decade, because 10 times before that the effect of pole starts, and this will still continue until this one. Okay, I hope you have already learned so much Bode plot that I don't need to write the ranges now. You can easily think through your mind. So yeah, the effect of 0 and pole both are present over here, so obviously they will cancel each other, so the slope will be 0 up until 1. Up until 1 the slope is 0. Okay, okay, slope is 0 degree per decade. Okay, so slope is 0 degree per decade. Now at 1 what is happening? The effect of 0 is going away. Okay, because 100 has been happened, like 10 times after this and 10 times before this the effect will remain. So after this the 0 is going away, but another pole is coming into effect, because at s equals to 10 minus 10 I have a pole, and obviously 10 times before this the effect of this pole will come up. So effect of two poles will be present. So effect of two poles is present. Then let me just wait, hold on a second. If the effect of two poles is present, then that means the slope here will be minus 90 dB per decade. Slope here will be minus 90 dB per decade, because two poles are present, right? That's why. Okay, next what is happening? Next at s equals to 10 the effect of this pole is going away, because 10 times after this and 10 times before this the effect will remain. After this the effect will go away, but this pole is still remaining here. And now what is happening? Now a 0 is coming to factor, because 10 times before this s equals to 10 the effect of this 0 will also come. So only single pole, effect of single pole is remaining, and effect of single pole 0 is remaining. So obviously it will cancel each other out, so my slope will be 0. Okay, so then at s equals to 100 the effect of this pole at s equals to 10 is also minus 10 is also going away, hence only this 0 is remaining. So obviously I will get a slope of plus 45 degree per decade. Okay, and then what will happen? Then obviously the effect of this 0 will also go away, then my slope will be 0 degree per decade. So let me write these things here. The slope is minus 90 degree per decade. Here the slope is 45 degree per decade. Here the slope is 0 degree per decade. Okay, so now from here it is 0 degrees. Okay, here it is 0 degrees. Now after this what is happening? It is going with the slope of plus 45 degree per decade, and it is traveling 1 decade. So obviously it will move up to 45 degrees, because one like that is what the slope tells. If I travel 1 decade, then I will move up by 45 degrees. So definitely the angle here will be 45 degrees. Okay, let me use this another marker. 45 degrees. Now the angle here is 45 degrees. Now after this, like this is at s equals to, so I need to move these points a bit. This point I need to move up. After this slope is 0, so it will remain constant. Okay, then the slope is minus 90 degree per decade, so it will move minus 90 in one decade. So it moves one decade and it has to move minus 90. So from plus 45 it will go to minus 45. Then what is happening? Then 10 times after this the slope is again 0. Then 10 times after this slope is again plus 45 degree per decade. So it will go to 0 degrees. It will go to again 0 degrees. Because we know that pole zeros are number of poles and number of zeros are same. So at s equals to infinity, the final angle will be 0 only. So it will somewhat go towards 0 degrees. Okay. I can do it like this also. So yeah, this will be the border part. So where is the maximum phase? Maximum phase is between this range, right? So maximum phase phi m will lie between this point 0.1 to 0.1 radian per second. Okay, so this will be my range for maximum phase. So this will be the answer. Like else you couldn't have been done with approximation. So okay, sorry, I'm doing one mistake. So not 0.1. It is between 0.1 to 1, because up here still it is increasing, right? Still it is increasing, but here the phase is remaining constant and it is 45. Obviously in actual case the phase will not remain constant. Okay, phase will vary a bit, but that is what the approximation does. Without even doing any difficult calculations, I'm able to tell you a good range within which my phase will lie. So if with the options you can be able to eliminate, if this question comes up in the gate, with the options you will be able to eliminate the maximum phase, right? Okay, so this will be the answer to this question. So omega should be lying between this 0.1 and 1. So yeah, now let's go to the next question. So in the next question, this is a very interesting question. This is a design problem. So just take the screenshot, okay, and like this is the first part, like and the continuation of this is this part, right? So you can take the screenshot or pause the video. You can simply try it for yourself. Then I will read the question and tell you about the like how to solve it. So first, you have been given the system, and it is desired that the behavior of the above closed loop control system as an underdamped second order system with like the behavior of the above closed loop system should be underdamped second order system and with particular performance parameters with settling time below 4 seconds and maximum peak overshoot below 8%. Okay, so these two conditions are there. These two conditions needed to be satisfied. So with the help of a proportional controller, find the range of kp to obtain the following performance parameter. Now you might say, sir, but we like you told us that we can't, like with proportional controller we won't be able to change the pole locations. Yes, we won't be able to change the pole locations, but if the pole locations are within the root locus, then obviously if that value satisfies our conditions, then obviously we can change, right? We can change the with the help of proportional controller we can change this parameters, settling time and the maximum peak overshoot, if those are within our root locus. I told you, right, with proportional controller we can only vary our pole locations, closed loop pole locations within the root locus. We can only go within our root locus. Okay, so that is what we will use. We will use the help of root locus, or we can simply use the help of route array as well. So we will use two methods to analyze this, right? So this is a very good question. So let's just totally focus on this question and like try to understand what I will do next. So first, like we are using a proportional controller and this is our OLTF. So we have to get settling time below 4 seconds. What does settling time mean? Settling time means like nothing is set, so we'll assume 2% error band. So 2% error band settling time should be equals to 4 tau. Okay, and what is tau? Tau in this case is, for a underdamped system, it is 1 by zeta omega n. Okay, 1 by zeta omega n. So what is zeta omega n basically? So if you recall correctly, for a underdamped system, my poles are complex conjugate, and j omega, and here I have minus zeta omega n, the real part, and here I have the two parts of the pole, right? Complex conjugate. The real part lies around here. So this is the what? This is the basically like real part of the pole, and the inverse, negative inverse of this is the time constant tau. Okay, so yeah, we already have derived this many times. So the settling time needs to be less than 4 seconds, below 4 seconds. So this has to be lower than 4 seconds, lower than 4. So my zeta omega n has to be lower than 1. Okay, so I will solve using two methods. So first I will solve using the Routh array. So zeta omega n is less than 1. So zeta omega n is less than 1. That means so my poles has to lie in this region. My poles has to lie in this region. If they lie in this region, yeah, sorry, I just realized that I made a mistake over here. So zeta omega n is not less than 1. If I like, that's why don't be in a hurry. So zeta omega n should be greater than 1. Okay, so zeta omega n has to be greater than 1. So if zeta omega n has to be greater than 1, that means my pole has to be like, this value is 1, so pole has to lie in this region. My poles, the complex conjugate poles should lie in this region. So if I break this down, okay, break this down, so my pole will lie in this region. So how to do this? So basically two things you can do. Either you can solve using root locus, or you can solve using this Routh array. So how to solve using Routh array? So my real part of my poles should lie on the left hand side of s equals to -1, because it is an underdamped system. So real part of SP should lie less than -1. Okay, as this is an underdamped system, obviously the poles will be complex conjugate. Okay, so basically now what will happen? Now we know one thing. With Routh, I can find that the condition for which some pole lie on the right hand side of my origin. Okay, but I don't know any condition for which at s equals to 1 some pole can lie on the right hand side. So that those I will reject. I don't know how to use that. So here we will use the concept of relative stability. So what is the concept of relative stability? I will just shift this axis here. I will move on to some other plane. So this is the S plane. This is the S plane. Whenever these types of questions come up, you can use the concept of relative stability and Routh array. So this is the S plane. What I will do is, I will go to a new plane, Z plane. Okay, I will go to a new plane. This is a Z plane, and in the Z plane what I will do, in the Z plane what I will do is, I will assume that this origin represents the s equals to -1 point. So my Z will be equals to s plus 1. Okay, my Z will be equals to s plus 1. So basically what can I see is, if I put s equals to -1, Z equals to 0. So s equals to -1 point represents Z equals to 0. So this is how the relation I'm mapping one plane to another plane. The concept of mapping is again coming from the Nyquist chapter. So Z is equal to s minus 1. So what I'll do, s will be equals to what? S will be equals to Z minus 1. Okay, so I will apply the Routh in the Z variable, not in the S variable, because I know around the origin I can talk about, but around -1 I can't. So I replaced S to Z. Okay, and now I will discuss about origin. So where I will apply the Routh, where we apply? We applied with the characteristics equation. So I have to write the characteristic equation. What is the characteristic equation? It is simply 1 plus KPS divided by S square plus 3 equals to 0. Okay, So this is my characteristic equation. So further if I simplify this will become s square plus kps plus 3 equals to 0. Now what we do, we replace s with z and then we will apply the Routh-Hurwitz criterion. So if I replace s with z, what will happen? S equals to z minus 1. So z minus 1 whole square plus kp into z minus 1 plus 3. So this will become z square minus 2z plus 1 plus kpz minus kp plus 3. And so this will be z square plus z kp minus 2 plus 4 minus kp equals to 0. So we don't need to use the Routh table. Like for second order I told you, right, we can directly use Routh-Hurwitz criterion from the this coefficients of s itself. So obviously all the coefficients must be of same sign. So here it is plus 1, the coefficient of z square is plus 1, so this should also be positive for it to be stable, for all the poles of this z plane to lie on the left hand side. And if all the poles lie on the left hand side of this z plane, then all the poles of the s plane should lie on the left hand side of the minus 1 line, s equals to minus 1 line. So kp minus 2 has to be greater than 0. That means my kp has to be greater than 2. Okay, now 4 minus kp has to be greater than 0. That means my kp has to be less than 4. Okay, so these two conditions are here. Kp has to be greater than 2 and less than 4. So for my settling time to be what? Less than 4 seconds. So this is the first condition only, kp less than 4 and greater than 2. Okay, so this is the first condition, and from here we can use the root locus. Okay, so now what else can we do? So basically the first range we found out for A, then how to solve this for the B part. So this is method 1. Let me write this as method 1. Okay, method 1 part A. Now how to solve the B part? So for B part, what you will do, like you don't need to do any intensive calculation, you had easily done this, right? So for B part, again I will use the characteristic equation, but this time I will use the characteristic equation of the S plane, because this time I don't have to use the relative stability. Just simply what I have to do, they have told us that the maximum peak overshoot should be less than 8%. Now what is the MPO a function of? Like what variable is from in what variable does the MPO is related with? It is related with the zeta. So MPO is a function of zeta. MPO is a function of zeta. If you remember the formula, it was e raised to power minus pi cot theta, or it is e raised to power minus pi zeta upon under root 1 minus zeta square. Okay, so this is how also you can remember. So now how do you find, like you have been told that your G like this should be less than 8%. So e raised to power minus pi cot theta, I will write in terms of theta. From there we can relate, should be less than 8%, which is 8 by 100. So I will just use the logarithm on both sides. If we just use the logarithm on both sides, what will happen? Ln I take 0.08 ln is okay. This is minus 2.5257 minus pi. Don't forget the minuses. Okay. Now if I multiply minus on both sides, what will happen? Sign like this inequality will be swapped, or I will move this one to this side and this one to this side. The signs will be swapped. Obviously inequality will be swapped. Like that also you can think. So my pi cot theta has to be greater than 2.5257. Now if I divide by pi, what am I getting? I'm getting cot theta has to be greater than 0.8. Now my cot theta is basically what? As the angle increases, what will happen? As the angle increases, cot theta is cos theta upon sin theta. So as the angle increases, cos theta will decrease and sin theta will increase. So hence overall this thing will decrease. So hence here this is not talking about the angle increasing condition. This is talking about the angle decreasing, because this has to be greater than 0.8. So if I increase my angle, this is reducing further. No, that is not possible. If I reduce my angle, what will happen? Cos theta increases if I reduce my angle, and sin theta reduces. The denominator reduces and numerator increases. Hence, overall this thing will increase only. So hence, this is talking about the condition where my theta is decreasing and not increasing. So if I am taking the cot inverse, that means my theta will decrease after the simplification. So if I like simply take the cot inverse, so here theta has to be less than this. This is the maximum value. If theta goes lower than this, then the cot theta will be more than 0.8. Just simply you solve. I will show you with one example. So just let me first find the value. So theta will be less than 51.2 degrees. Okay, so theta is less than 51.2 degrees. Now basically we are interested in the zeta. Okay, but let's first do the example. So theta has to be less than 51.2 degrees. So let's assume theta equals to 45. So if I assume theta equals to 45, sin 45 1 by root 2, cos 45 1 by root 2, which is 1, which is satisfying this condition. So yeah, this is correct. The theta has to be less than this. If I assume something more than this, this will be less than 0.8. So let's assume theta equals 60. So sin 60 is what? Root 3 by 2, and cos 60 is 1 by 2. Okay, 1 by 2. So 1 by 2 by root 3 by 2 is 1 by root 3, and 1 by root 3 is from what I remember 0.557. Let me just quickly cross verify. 0.577 I think. Yeah, 0.577. So which is less than this point. Obviously from here also you can understand that theta cannot be more than 51. Theta has to be less than 51. So yeah, just take few examples and you will understand. So this is the first case. Now let's write the condition about zeta. So if theta is reducing, that means what? Theta equals to cos theta. So cos theta will increase. So zeta has to be greater than something. So if I take the cos on both sides, then the inequality will interchange. Okay, that is the reason. Because as theta increases, cos theta reduces, or as theta reduces, cos theta increases. Okay, so if I take the cos of this angle 51.2.626, so my zeta will be simply zeta has to be greater than 0.626. I'm just simply taking the cos on both sides. Okay, just simply taking the cos on both sides. So yeah, this is the thing. So now let's this is the condition that I need to get, right? Zeta has to be greater than 0.626. Now let me write the characteristic equation in the S domain. So what is the characteristic equation in the S domain? It is simply this only, right? Kp into S by S square plus 3. So 1 plus Kp into S divided by S square plus 3 equals to 0. Okay, so this will be S square plus Kp S plus 3. Now what is important here? So this is the closed loop this characteristic equation. So omega n is this omega n square, and we are not interested in the omega n square. Omega n is under root 3. Okay, and what is 2 zeta omega n? 2 zeta omega n equals to my Kp. So zeta omega n equals to Kp by 2, or zeta equals to Kp by 2 omega n. Okay, now this has to be greater than 6.626. Okay, so I hope you got the understanding that why zeta has to be greater than this, because intuition you can understand your peak overshoot has to be less than 8%. So zeta introduces damping. So damping reduces the overshoot. Okay, damping reduces the oscillations. So obviously zeta has to be greater than this. If zeta reduces, the oscillation will increase, the peak overshoot will increase. Obviously we don't want that. We want to reduce the peak overshoot. Okay, peak overshoot has to be less than 8%. So that is the reason. Now also you can understand that zeta has to be greater than sign. Okay, or simple angle thing I have told you, right? With intuition you can understand. Yeah, sorry for the interruption. Actually some like important person came, like delivery boy came, that's why I have to again pause the video. So basically my zeta has to be greater than this, right? Zeta is this, so it has to be greater than 0.626. It has to be greater than this. Zeta has to be greater than 0.626. Okay, so if zeta is greater than 0.626, that means that kp will be what? Kp by 2 under root 3 omega n is under root 3 has to be greater than 0.626. So basically my kp has to be greater than this into 0.626. so kp has to be greater than 1.2.17. okay, so obviously kp has to be greater than this, but there is a upper threshold for kp as well. If you can observe here carefully, the maximum value kp can go to is 4, because if kp goes more than 4, the settling time condition will be violated, so we don't want that. So kp should be greater than 2.17 and should be less than 4. So this is the valid range for this. Okay, so with the help of root locus we can simply solve this. So like next we'll solve with the method 2, which is the, sorry, with the help of this route we can simply solve this. Now next we'll solve with the root locus method. Okay, so before that I'm really hungry, so I will just eat something and then I will solve with the root locus method. Method 2, root locus. Method 1, route service. Okay, so what is the root locus method? So first I will write the OLTF. What is my OLTF? OLTF is kps by my like g of s, where my kp is the variable s square plus 3. Okay, so can we plot the root locus real quick? So here if I want to plot the root locus, sigma j omega. So here where are my zeros and poles? So 1 0 is at the origin, okay, and 2 poles are on the imaginary axis, j root 3 and minus j root 3, j root 3 and minus j root 3. Okay, so how will this behave? Will this go on the right hand side or will this go on the left hand side? Obviously from the route array I can say that this will obviously go in the left hand side, but if you, let's say if you don't know the route array, how will you do? So where will another there are 2 poles, number of poles is 2 and number of zeros is 1. Obviously there will be one virtual 0. Now where will that virtual 0 lie? Basically where will that asymptote lie? So if I want to calculate the angle from the angle of asymptote thing, you can understand, or from this first condition is that on the right hand side of my test point, the number of poles plus 0, summation of poles plus 0 should be odd. So if I choose this as test point and on the right hand side I check that I have odd number of poles plus 0. So obviously all of this, whole of this negative real axis is lying on the root locus. So obviously all of this will lie on the root locus. Okay, and next what will happen? Next obviously what will happen is basically they will start they will start the root locus. They can't go this side, because if they go this side they have to break in some point. If they break in some point, then they have to again follow here, but this is not a valid point in the root locus. Why? Because if I choose this as test point and I check on the right hand side, I check that I don't have any poles or zeros. So number of poles are 0 equals to even, which is not possible. So obviously if they come in from here and break in somewhere here, so this is a valid, this does lie in the root locus, so this is a valid point. So obviously this can't go this side, this will have to go this side, or you can do it from the angle of departure formula, that you can do. Okay, and obviously from the break-in point also you can understand. Okay, or from where else you can understand from the angle of asymptote. So what is the angle of asymptote in this case? Angle of asymptote will be minus 180 p minus 0 by 2 minus 1 into 2n plus 1 where n equals to 0 only. So if I put n equals to 0, it will be minus 180. Obviously my asymptote will lie here, okay, on the negative real axis, okay, at infinity. Okay, so this will be like something this, that this will come here and then this will break in, okay, and then this will come here and this will break in. Okay, now the thing is, the beauty of this is like you will observe one thing. I will tell you, you first try to observe if you can observe that thing or not. So later I will tell you what is the beauty of this. Okay, so basically what I can say is this point is root 3, this point is root 3. So let's find the break-in point. What is the break-in point? So for break-in point I will again use that same Kisa-Pita formula. So what is the Kisa-Pita formula? That formula is A of s, the numerator is simply kps, and b of s, the denominator is simply s square plus 3. Again I will differentiate this. A dash of s equals to kp, b dash of s simply equals to 2s. Okay, b dash of s is 2s. Now what next we'll do? Next, basically what I can do, a of s into b dash of s, so and like minus b of s into a dash of s. So a of s kps into b dash of s 2s minus b of s s square plus 3 into kp a dash of s kp equals to 0. So from here obviously like kp can't be equal to 0, so I can eliminate kp. So 2s square minus s square minus 3 equals to 0. So my s equals to under root 3. I will eliminate plus 3 because this will come as plus minus 3. I mean I will eliminate plus 3. Why? Because this is not a valid point on the root locus. S equals to root 3 is not a valid point because here no point can lie. Okay, so here the break-in point is minus root 3. Okay, I'm just drawing the root locus for now, that's why this is lengthy. Okay, just bear with me. So next what I observe is that this is the distance from here is root 3, the distance from here is root 3, the distance from here is root 3. So this will form a circle. Like don't go with the diagram, this is not looking like a circle, but this will actually form a circle. Okay, so the distance will always be root 3. Okay, distance will always be root 3. Just hold on a second. Distance will always be root 3. Okay, so the distance is root 3. Basically what does this mean? This means that like this is a circle. So but what condition we have to find? We have to find that my zeta omega n should be greater than minus 1. That I have already established. Okay, all the poles should lie, like real part of the pole should be greater than minus 1. So let me just draw the line. This is minus 1 line. Okay, this point. So all the poles has to lie left hand side of this. So if all the poles lie left hand side of this, then this will still remain a underarm system. Okay, so basically let me mark the arrows direction of root locus, going here, here, and this is going here and here. Okay, so basically what will happen, this is going here and this is going here. Okay, so now what will happen? Now what I have to do is all the roots should lie on the left hand side of the -1, this line. So here what I can do, I can take up a line from here. So if I take up a line from here and if I mark this as theta, let me just mark this as theta. Okay, or let me mark this as something else. What should I mark? Let me mark this as alpha. Okay, angle is alpha. So if this is alpha, now this distance I know is √3 because this is lying on the circle. So this distance will be √3. Okay, and this distance from the origin is 1. I'm talking about the distance. Okay, I'm talking about the distance. This distance is 1. So if this distance is 1, okay, this distance is 1 and this distance is √3, then what do I have to find? I have to basically find the values of k, right? I have to basically find the values of k. So for that, what I have to do is I have to find this root location. I have to find this root location. So what was the value of k up here? So if I just check one thing, like for this s equals to √3, the value of k. So I just put s equals to √3 in this equation. I will find the value of k. Okay, not in this equation, sorry, in this equation. 1 plus kp √3/3 plus 3 equals to 0. So my kp will be simply equals to 1 plus g of s. Sorry, it was minus √3. Sorry, it was minus √3. So this kp will be equals to this minus goes on this side plus 6 upon √3. So 6 upon √3 is 2 √3. So my kp is simply 2 √3. Okay, so if my kp is 2 √3, what is the exact value? 3.46. So it is 3.464. So at this junction my kp is 2 √3. Like obviously what you do is you don't solve with this in the exam hall, like in this method you solve with the route array because that is much easier. This is just to clear up your concepts, many concepts, and get a good grip, right? That is very important. Like this concept may be used in some other question. Okay, maybe you can use this method in some other questions, so it is very important to bear with me right now. Okay, so this is √3 and this is -1. So let me just draw the triangle. Let me just draw the triangle. This is alpha, this is √3 and this is 1. So what will be this? This will be simply, this distance will be simply √2 because √2 square plus 1 is under root, that is √1. So this is √2. So I can find my pole locations now. So the height of this point is just hold on a second. If I can use some other color, I can't use some other color. Height of this point is j√2 and the distance, like x coordinate, is -1. So -1 plus j√2 and another root will be obviously complex conjugate here, -1 and plus j√2. So obviously real part is -1, but all other things has to lie within this. Okay, all other things has to lie within this region. Okay, within this region. So what I can do, I can find the value of k over here. I can value the k over here. So k is starting from here, k equals to 0, and it is increasing. Okay, so after this point it has to increase further. This is the minimum value of k. Okay, minimum value of k. After that we'll find the maximum value also. So I will just, how to find the value of k, simply put that pole location in the characteristics equation. 1 plus kp into -1 plus j2 divided by -1 plus j2 whole square plus 3 equals to 0. Okay, so kp into -1 j root 2 divided by 1 minus 2 minus j2 root 2 plus 3 equals to minus 1, and kp will be equals to simply this is minus 1 plus j root 2 and this is minus 1 2 minus j root 2, so minus 1 will be here, kp will be simply equals to 2 itself. Like just if I can write this will be kp into minus 1 plus j root 2 divided by 2 minus j2 root 2. Now if I take the common 2 over here, my common minus 2 over here, this will get cancelled and minus 2 will go in the denominator, and minus 2 multiplied by minus 1 will be 2. So kp will be 2 and kp has to be more than 2. Kp is increasing, okay, kp is increasing, okay, so kp has to be more than 2. Now what is the limiting value? One thing you observe is that when I reach this point, there is a break in point. Yeah, actually sorry for the interruption, like some call came up. I was saying that these two, like out the root locus will leave from these 2 points and will meet at these 2 points. So there is a break in point here and then they are separating. Okay, so they are breaking in here and then they are separating. They are not breaking out, they are breaking into the this real axis. That's why it is known as break in point. So now after this, what is happening, interesting fact is that one pole is going more towards the minus 1, another pole is going more away from the this minus root 3, right? So if this is going more close towards if this pole is going more close towards the minus 1, then this will be the dominating one and this will be the non-dominating one. Or if this is the non-dominating one, that means like we can ignore that. Okay, we can ignore that and I can calculate my settling time with only this. So at certain point, after this passes through this minus 1 point, then my settling time will be what? Will increase the 4-second threshold. For like I told earlier, right? All my poles should lie on the left hand side of my minus 1 line, but some like one pole will go will go after this minus 1 comma line near this origin. Okay, so obviously k is increasing, so the maximum value of k will be this when one of the pole is at s equals to minus 1. Maximum value of k will be this. So if I write that at s equals to minus 1, k will be kp max. Okay, kp will be kp max. Okay, because kp is obviously increasing. Okay, I will terminate at zeros. So obviously after that, the pole real part of the one of the pole will be less than minus 1, which is not desired. The settling time will increase. So basically I will put s equals to minus 1 in this simple characteristics equation. Minus 1 whole square plus 3 equals to 0. So kp will be simply equals to 4. So kp max, this is not kp, kp max equals to 4. Okay, so what is the range of kp? Kp range is between these two, 4 and 2. Okay, so this is for the case A. Case A. Okay, case A. Okay, I mean not the case A, for the part A. Now let's solve for the part B. For the part B, again some interesting fact. Like I've already solved it. Okay, about the angle condition I have already done. I won't repeat it. So my angle from the negative real axis should be less than 51.2 degrees. So here if I mark this angle, if I just do one thing, just copy this. I have already found out previously that my angle for the peak overshoot to be less than 51.2%, it has to be less than for it to be less than 8%, it has to be angle has to be less than 51.2 degrees. Okay, 51.2 degrees. So my angle has to be less than 51.2 degrees. What does it mean? It means that if I draw a line over here, my angle should be between these. Like some question came in gate 2024, just similar to this pattern, just almost same to this pattern. So my maximum angle can be this 51.2, angle has to be less than this 51.12. So I will just find the pole location at that point and I can get my value, right? I can get my value. So obviously angle has to be less than 51.2. So this value is what? This value is root 3 because it is a circle. It is a circle, so the distance will be always root 3. Now I can find the x and the y coordinates, and from there I can find the pole location. So my SP will be basically simply root 3 times cos 51.2 plus j sine 51.2 degrees. And obviously this is the maximum point. After this, obviously what will happen, like as this k increases, the zeta will increase. Okay, zeta will increase, or the angle will reduce. You can say angle will reduce. So I want my angle to be less than this. So obviously this is the, so not the maximum, this is the minimum value of k. Yeah, sorry, the iPad keep getting crashed. Okay, so what I wanted to say is the angle, like the angle has to be less than 51.2 as proved earlier, right? The theta angle from the negative real axis has to be less than 51.2. So if it is less than 51.2, that means the k value is increasing from here. K is 0 over here and it is increasing. So k has to be something more than this point. This is the lower limit of k. This is the lower limit of k. K has to be something more than this. So I have to find the value of k at this point, and from there I can derive. So you can use the root locus for a proportional controller always. So basically what you do is you find the root location. So root location finding is very simple. You know this and you know this angle. So simply you will find the root location, and this will be the minimum value of k, kp minimum. Okay. So root 3 times cos 51.2 51.2 cos into 3, it is 1.08 plus j, then 3 root into 51.2, 3 root into 51.2 sine, so 1.35 SP. Okay, so this is 1.08 and plus j 1.35. Now you just put this value at that equation. Okay, so if you put this simple value at that equation, you will get your pole location. Sorry, you will get your kp minimum. So basically again 1 plus kp minimum is 1.08 plus 1.35. You can solve using the graphical method also, no issues. You can solve using the graphical method also, like the distance between this point and distance between this point and this point. Okay, you can solve using that graphical method also. I'm not using that. I'm not using that for now. I'm directly solving on the equation. So this will be s square. So 1.08 whole square minus 1.35 whole square plus 2j 1.08 into 1.35, which is equals to 1.45 458. Then here it is equals to simply what it is equals to, then we have that plus 3 as well, right? Plus 3 as well equals to 0. So how to solve this next? Like this will be a bit tedious task. What you can do is you can use the magnitude condition, the magnitude of this whole thing, right? The kp minimum, as this lies in the root locus, I can use the magnitude condition. Magnitude of this 1.08 plus j 1.35, which is root 3 itself. We know this because obviously from there it was derived, and this is what this is. Let me do this 1.08 whole square. So this is more calculation intensive, and that is fine. You will learn a new method. Plus 3 is 2.344, and this is 2 times 1.458. So this is plus j 2.916. Okay, so check, you will see that this is equals to 1. Magnitude of this whole thing will be equals to 1. Hence this magnitude is root 3 itself. K minimum should be equals to root 3, and in the numerator what will be it? Square plus 2.344 square under root is 3.741. If I divide this with root 3, I get 2.16, which is nearly equal to the previous one, as we saw from here, right? Kp minimum, if you recall, yeah, almost this. Kp minimum is this 2.71. So like, yeah, it almost like just put one decimal here and there. So Kp minimum is this, and we found out that here my Kp maximum is 4. So Kp minimum is 2.17. So my Kp has to lie between this. Kp has to lie between this 4 and this 2.16 and this 4. Now one thing we missed out. Can you say that what did you miss out on? We miss out on one thing. What did you miss out? We missed out that Kp can't be more than 2 root 3. Why? If Kp is more than 2 root 3, that means here in the question they mentioned as an underdamped second order system. Okay, this is very important, as an underdamped second order system. So that's why this can trick sometimes. Okay, this root locus method can trick sometimes, because from here you can't know the behavior of the system. Okay, you can't know the behavior of the system. If you for some reason put Kp equals to 4 and then calculate the value of zeta will come out to be more than 1. Okay, you put Kp equals to 4 in this equation, you put Kp equals to 4 in this equation, what will zeta come out to be? If you put like Kp equals to 4, s square plus 4s plus 3 equals to 0. So that is what we missed. So here my zeta will be what? Zeta will be 2 zeta omega n is 4, so 2 by root 3, which is more than 1. Root 3 is 1.732 and 2 by is more than 1, so which is greater than 1. So that means my system is over damped, which I cannot allow. So obviously from this condition also you could have said that I cannot allow this condition. Okay, so what will happen here? What will happen is my s square plus kps plus 3 equals to 0. So my zeta at max can become 1, equals to 1. At max it can become equals to 1. Okay, that is the limiting condition. Zeta less than 1 is underdamped. So if my zeta is 1, zeta maximum equals to 1. That means 2 times zeta max times omega n, which is root 3, which is constant in our case, is Kp. Okay, so Kp max can go to 2 times 1 into under root 3, so 2 under root 3. Okay, so Kp max can be 2 under 3, which is 2 times, so it will be 3.46, and zeta between this sorry, I made the mistake. This will shift to that side and this will shift here, 2.17. okay, so this is the value of zeta. Okay, so just be careful about that. So like we can get tricked, and this is a very good question. That from the root locus also you can understand that the root locus is coming over here. After this, what is happening? The poles are negative and unequal, real negative and unequal. That means from underdamped it is going to overdamped, because here it is critical damp at this particular point and then it is going to overdamp. So obviously we want our system to be underdamped. That is the desire of us. So at max Kp can be 2 root 3. It has to be less than that for it to remain underdamped, because for the poles to be complex conjugate. So from the root locus I can say locus system for system to remain underdamped, it has to be basically K max can be from the root locus, I can say 2 root 3. Okay, so obviously from here also I can say the range will be 2.16 K to 3.46. okay, 464. So this will be the answer of this question. This is a very good question. I know I took a lot of time, but I hope you got more things clear, and root locus also got revised, route array also got revised. That is the main motto, right? That is the main motto. So that if from this lecture also you can revise the previous things. Like time domain analysis got revised, root locus got revised, route array got revised. So this controllers and compensators chapter is very important. That's why it is asked in the interviews, because everything can be asked from here. This is a very good question. Okay. So what I will do is I will give this question as homework to you. Okay. And I will solve this in the next lecture, because this lecture has already gone long and this will take more time to solve this. So I'm giving this you as homework, and in the next lecture I will solve this as an extra question. Okay. So thank you for watching, and this is almost the end of control systems lectures. So the control system has almost been ended, and this is the last question that I will solve of control system. So I hope you like this series, and if you are one of the last few remaining soldiers who have survived and come at the end of this series, then I'm proud of you, and I hope you can score 100 out of 100, 100% marks in control systems at least. For your gate, whatever examination you're preparing, you can score 100% marks, because I've given you almost all the concept that is required to crack gate for control systems and other competitive examinations where control systems is asked. So this is the last question that I will solve. Okay, so yeah, thank you for watching. I will see you in the next video.